Hi everyone! Today we will be looking at the mechanics of prosthetics. So what is a prosthesis? A prosthesis is an artificial body part. Prostheses are most commonly used by amputees in order to regain movement or function. Prostheses have to be made out of strong yet lightweight materials so as not to encumber the user, but to be able to bear weight. They are commonly made out of aluminum, titanium, or stainless steel. Although there are many different types of prostheses, today we will be specifically looking at the mechanics of the prosthetic leg. Some general assumptions that we will be using throughout the video are that the prosthesis is made out of titanium and that its user weighs 70 newtons. First, we will examine the mechanics of an individual with a prosthetic leg while they are standing. The diagram on the left shows that each leg bears approximately half of the weight of the user. Thus, the internal normal force in the leg is also approximately half of the weight of the user. Assuming that the prosthesis has a radius of 1 centimeter and the user weighs 70 newtons, the stress in the prosthesis would be 0.11 megapascals. Since titanium has a tensile yield strength of around 800 megapascals, it is a good choice for prostheses.
The human walking gait cycle consists of a stance and swing phase to make up the entire stride. This walking stride takes on a similar motion as that of an inverted pendulum. In this problem, the prosthetic leg is on the shaded side where the heel is in contact with the ground. Using given values, we are going to compute the force exerted by the quadriceps, as well as the normal force and moment about the knee. In the free body representation of the knee, the force of the quadriceps, Q, the weight of the individual, W, the normal force, N, and the moment at the knee, Mk, is represented with their appropriate directionality. Using the free body diagram drawn in on the right of the knee component, as well as equations of motion, the unknown values are computed. As the body is rigid and in equilibrium, the sum of the forces in the x and y will be equal to 0. An axis of reference is also included to distinguish positive versus negative values. For the sum of forces in the x, only W and Q have an x counterpart where their signs are indicated by their direction according to the original frame of reference. Therefore, by substituting known values, the force in the quadriceps is computed to be around 70 newtons in the indicated direction. Next, doing the same with the sum of forces in the y, also equal to 0, all values in the sum except for n are known after solving for q. So by substituting values and rearranging the equation, the normal force at the heel comes out to be 0 newtons. Lastly, the sum of moments is found by multiplying the forces by their distances from the point of summation. In this case, as the normal force is directed vertically, the horizontal distance is multiplied with the magnitude of n, which equals 0. Hence, as the only force that was working on a distance away from the point of summation was n, there is no subsequent magnitude for the moment about the knee in this particular problem, given the provided values.
This is an image describing the running gait cycle of humans. Roughly 70% of the human running gait is in swing phase, while the other 30% is in stance phase. These phases can be seen highlighted above in red, where the shorter one is a stance phase and the longer one is a swing phase. The three stances underlined in blue represent the aerial phases, in which both feet are off of the ground. For this example, we will be focusing on the second gait, called mid-step. We will continue operating under the same assumptions in the previous question, in which no friction is present at the knee joint. We will focus on the image above, in which one foot is planted on the ground and is pushing up to go into the next step. The free body diagram can be seen to the right, in which the length of the quadriceps is assumed to be 0.2 meters, and the length of the lower leg is assumed to be 0.4 meters. The positive direction of x, y, and the moments are indicated in the upper right corner. We will be focusing on the force about the knee, so we will need to find the pulling force of the quadriceps. The weight of the person is 70 kilograms and all of their weight is currently on their leg, so the weight distribution does not need to be taken into consideration. The moment about the knee is indicated by the blue arrow. A moment is a tendency of a body to rotate about a specific point, which is very important to consider when doing biomechanics for weight-bearing limbs such as the legs, as the prosthetic cannot buckle and must be able to help the user balance. We are now going to calculate the forces in the x and y direction as well as the moment about the knee. We will not be assuming the body is rigid for this problem, so we will be using equations of motion to calculate the forces about the knee. We will begin by calculating the force of the quadriceps on the knee using the equation the sum of forces in the x direction is equal to the mass times acceleration in the x direction. For this problem, we are assuming the acceleration in the x direction is 1.5 meters per second squared. Using the indicators for positive and negative directions, one can set the forces in the x direction equal to quadriceps force times cosine theta minus the weight times cosine theta. Solving this equation results in a quadriceps force of 210 newtons. The same process is repeated for forces in the y direction to find the normal force. This equation results in a normal force of negative 51.25 newtons. In the third equation, the moment is equal to inertia times angular acceleration. Solving for inertia gives a value of 3.73, and plugging that in results in an angular acceleration of negative 5.5. Alpha is angular acceleration, which indicates the speed of rotation of the knee. The angular acceleration being negative means that the knee rotates in a clockwise direction, which can be expected. Even amongst aluminum and other commonly used materials for building prosthetics, titanium is an ideal metal with its lightweight capabilities, as it can easily handle the forces required by it to perform everyday movements. As the three examples in this video showed, a strong lightweight material is needed, and titanium is one of the best options. Biomechanics has a massive field that has greatly improved the lives of millions of people. It extends from tissue engineering to prosthetics to smartwatches and phones, and the innovations from the biomechanics field touch the lives of everybody on this planet.